Consider the linear system Px plus F. This is a linear system of ordinary differential equations, and suppose x sub p is a particular is a solution called a particular solution, then every solution of this linear system of ODEs can be expressed as a linear combination that involves this particular solution. So then every solution has the form x equals x sub c plus x sub p, where x sub c is a solution, or where x sub c solves the problem, the homogeneous problem, which in this case would be dx dt equals p of x plus 0. In other words, x sub c is a solution of the homogeneous problem. X sub c solves derivative of x vector equals p times x. So this x sub c is a solution of the homogeneous problem. So So let's discuss an example about this. So let's consider well, this example is still about homogeneous, but let's this is an example of so let's consider dx1 dt, dx2 dt. So this is x1, and here this is x1 minus x2. And the initial conditions are x1 of 0 and x2 of 0. x1 of 0 is 1, x2 of 0 is 2. So this example is not quite illustrating that theorem. This example, let's write in a matrix form, and then that will become more clear, right? So in matrix form, matrix vector form, we write the derivative of the vector state variables x1, x2 equals matrix times vector plus a vector of zeros. So you'll see that in a minute. So here we have the first function is 1x1 plus 0x2. So we can write a matrix 1, 0, And the second equation is 1x1 minus 1x2. So the second row has entries 1 minus 1. So we can write this matrix with column 1, 1, first column 1, 1, second column 0 minus 1, multiplying the vector x1 and x2. I think we have probably worked these out before. So the eigenvalues are off the top of your head by inspection. This matrix is triangular. There are zeros above that lower triangular part. So if you compute the determinant of this matrix, you're going to end up multiplying the entries on the diagonal. So here the eigenvalues are dot, 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 lambda 1 equals 1, and lambda 2 equals minus 1. Because it's triangular. If it were not triangular, then we'd have to do the characteristic polynomial, you know, all that. Now, the eigenvectors, let's see. Well, let me write this. It's not too complicated, so the first row we said was 1 and 0, and the second row has 1 and negative 1. Is that correct? So let's see what this matrix looks like. So we define the matrix over there, and that's the matrix, right? That's the matrix. First row 1, 0, second row 1 minus 1. So I'm going to use this command, eigenvectors right, for that matrix. A So we have eigenvalue 1 has eigenvector with entries 1, 1/2. So I was saying that lambda 1 is 1. So let me write here. Lambda 1 is 1. Let's see. Lambda 1 equals 1. And V1 has entries 1, 1/2. The second eigenvalue is negative 1, and it has an eigenvector with values 0, 1. And so here you can say lambda 2 is negative 1, and V2 has values 0 and 1. There you go, 0 and 1. So if those are the eigenvalues, so the eigenvalue 1 has corresponding eigenvector 1, 1/2. The eigenvalue minus 1 has corresponding eigenvector 0, 1. And I can write now the solution of the homogeneous problem. We can write the solution as, well, you see that in this case, the imaginary parts of the eigenvalues are 0, right? So this is 1 plus 0i, and then minus 1 plus 0i. So e to the lambda 1t and e to the lambda 2t, those calculations are simplified because the imaginary part is 0, and therefore no need to apply Euler's equation. Well, if we apply Euler's equation, it's trivial. So here, e to the lambda 1t becomes e to the 1t, e to the lambda 2t becomes e to the minus t, and therefore e to the lambda 1t times v1 will be e to the t times the vector 1, 1/2 is vector v1 with entries 1 and 1/2, and also e to the lambda 2t v2 is e to the minus t times vector 0, 1. So e to the lambda 1t v1 becomes a vector with entries e to the t over 2, while the other calculation, e to the lambda 2t times v2, becomes a vector with entries 0, e to the minus t. And what we would like to do next is to take the linear combination of v1 and v2, right? So the solution that we're going after, the so-called x sub c, is something that looks like c1 e to the lambda 1t v1, c2 e to the lambda 2t v2, otherwise c1 times this vector et over 2 plus c2 times this other vector with entries 0 e to the minus t. And this would be xc1 and xc2. The first entry of x sub c and the second entry of x sub c will come out of this calculation. But we should also make use of the initial conditions, right? If we evaluate the initial conditions, we can use these values for x1 and for x2. x1 at 0 is 1 and x2 at 0 is 2. So using initial conditions, we're going to get 1 equals c1 plus c2, let's see, are 1 and 2, so c1 e to the 0 is 1, and this is 1/2, and this is 0, and this is 1. So we can find these values of c1 and c2 by doing something similar to what we did, right? So we could, here we have two equations and two unknowns on these constants c1 and c2. So we could form a matrix with columns 1, 1/2, 0, 1, and then I'm going to put these values here at the end. We can form this matrix and we could row reduce to find the values of c1 and c2. Form a matrix and row reduce. That's what I'm going to do here. Previously I had done it by hand. Here, since in the spirit of illustrating this yet a little more, so I'm going to call this matrix C. This matrix is going to have two rows, okay? So I'm going to write it in terms of rows. the first row I list the values inside square brackets and then I separated the values by commas. The first row has values 1, 0, 1, and the second row has values 1/2, 1, 2. So there is a matrix we want to row reduce. So that's what I'm gonna write here. C RREF. That's the command RREF, reduce row echelon form. And so the reduce row echelon form tells us that this specifies what are the values we're going after. Okay, so this here has RREF of the form 1, 0, 1, and then 0, 1, 3/2. So this implies that C1 equals 1 and C2 equals 3/2. So in other words, we can go back and write the solution with coefficients 1 and 3/2. This value here would be equal to 1. This value of C1, here we would write number 1, and here in terms of writing C2, we would write 3/2. Actually, here's where we need to do 1 and 3/2. 1 and 3/2, which means the first entry is going to be 1 e to the t plus 3/2 times 0, which is 0. So the first entry would be e to the t. The second entry would be 1 e to the t over 2 plus 3/2 e to the minus t. Second entry looks a little more involved, but after doing this substitution, then we obtain that the complementary solution of the homogeneous system becomes e to the t for the first entry, e to the t over 2 plus 3 e to the minus t divided by 2 for the second entry. This vector, this entry, this et and this et halves plus 3 e minus t halves, these are the equations. I said x sub c, which is probably poor choice of. So this would be x sub c 1, and this would be x sub c 2, the first entry. So these are the functions. X sub c1 of t would be e of t. X sub c1 of 2 would be this sum. Those are the functions of t that satisfy these equations with these initial conditions. And what I really meant was to work out an example of the non-homogeneous type of formulation, but this is the example we have in this part of the textbook, right? So, in fact, earlier on, these equations are a little special because the first differential equation here has only x1. So x2 has a coefficient of 0, therefore x2 doesn't appear in the first equation. That means these equations are decoupled. That's a word, decoupled. And then there is another trick about finding the solution of this. You could read about that. I chose to do here in class something that's more elaborate in terms of using the eigenvalues and eigenvectors, and something that is yet illustrating once again this business, that the solution is a linear combination of the eigenvectors, and the coefficients on that linear combination involve the evaluation of the exponential at each of the eigenvalues, right? So it's this idea of the eigenvalues and eigenvectors coming together to offer a solution of the homogeneous linear system of equations.